Bon, je pense qu'on peut commencer. So it's a great pleasure to welcome Immanuel Bloch for this seminar. As you know and have seen in the first part of these lectures, Immanuel has been a true pioneer of this field. He's in particular one of the co-authors of this famous 2002 paper realizing the superfluid two-mode insulator transition in optical lattices. Since then, he has done remarkable work on many fronts of this field. Immanuel did his PhD at the Ludwig Maximilian University in Munich. And since then, he has been a professor in Mainz, and as you all know, he's now a director at the Max Planck in Garching and also a professor at the LMO. He has had a very large number of distinctions, which I'm not going to enumerate one by one, but just maybe I'll mention two: the Leibniz Prize, which is a very prestigious prize in Germany, and I also want to mention one which intrigued me very much, which is the 2021 Bavarian Maximilian Order for Science and Art. Beautiful title.
Yeah, it's actually a real honor.
So, but more importantly, Immanuel is a wonderful scientist. So let's welcome him, and thank you for accepting the invitation.
Yeah, thank you. Thanks, Antoine, and thank you for the invitation. It's always a pleasure to be in Paris among so many friends and colleagues. Wonderful to be here, and I was really also excited listening to Antoine's lecture. I hope I can connect to a lot of things he's been talking about. So I see it's quite a mixed audience, some experts of the field, some maybe who don't know the field so well. So let me start and give you a little bit of an introduction into quantum simulation and actually what we measure in this quantum simulation approach, what we can measure, what we plan to measure in the future. And then jump, for the main part of the lecture, jump right into what Antoine has been talking about, trying to connect what kind of problems we can look at with these quantum simulators of electronic systems mostly, and then finally give you a little bit of an outlook. Also connect this, we've been doing a lot of actually recent developments towards gates. We'll show more quantum computing based approaches with fermions. I think actually these marry very well together, as you'll see, as they also give us really unique readout and preparation capabilities. So just to, what happened to my title? So just to give you a brief overview again of analog and digital, the two sides of the quantum any-body world that people are exploring now. In quantum systems, you have quantum simulation approach, what we're going to talk about mostly here, or a gate-based approach would basically try to do the same thing, solve interesting many-body problems in material science or chemistry, for example. And the two are quite distinct from each other. We make quite good use of the resources of the hardware in the quantum simulation approach, but typically are not universal. On a digital quantum computer, we hope to be universal, but of course this is extremely resource hungry if you think about the requirements for fault-tolerant error correction. Now, actually, one interesting thing, Ignacio is going to be talking later today, and I think actually he might even touch upon this topic. I want to raise an issue that people have been talking about, namely, what about the error resilience of this quantum simulation approach? Isn't it a problem that you have, your matrix elements, the couplings in the system, they all have finite errors, and if you scale with system size, this is an extensive amount of errors in the system that you're making. So how can this simulation still give some faithful thing that comes out of this? It turns out that mostly because the quantities, the physical quantities we're looking at are actually intensive quantities, not extensive quantities, that this approach is actually quite robust. And to put that on mathematical grounds, this was actually done in a recent paper together with Raúl Trivedi and Ignacio, who showed actually that this approach is indeed rather robust. And also they showed on mathematical grounds what it actually means to have and achieve quantum advantage in such a setting of quantum simulation. So I just advertise his talk, probably might talk about that. If not, this is a really nice, I think, important paper for the entire field. As Antoine said, for me, the starting point was this original work on superfluid to mod like over 20 years now ago. And this really, I think, sparked off the field of quantum simulation, which people are now pursuing in a wide variety of platforms, from ion traps, lattices, the wonderful work on tweezers here, especially in Paris, Antoine's group, and also here at Collège de France, superconducting devices. You know, I think it's become a major research field across all of these different platforms. So for us, we're working in the optical lattices. We're working with fermions, bosons in these systems, and we create them by interfering laser beams. Here you see a nice pattern from Ted Hensch, this quasi-crystal structure coming out of 5 interfering laser beams. And we can put atoms there which have different hyperfine states, emulating spins of electrons in the system, or use electronic degrees of freedom, for example, on a clock transition in strontium, which would again mimic like 2 degrees of spin degrees of freedom in the system. Typically, we work with hundreds or thousands of particles. And again, the unique aspect, I think, of the atoms is that you can have fermions. This is, of course, the main topic for us here. The only other platform I see where this is done is actually quantum dot community, which are also working in this direction. But all other problems, you basically, whenever you want to simulate the physics of electrons or fermions, you have to do some mapping, some encoding, which requires some overhead in the system. So in terms of lattices that you can realize, the community has been quite flexible, and we've thought for quite some time that you always need to interfere their laser beams at different distances and angles to create these different lattices. By now, a couple of groups have developed actually techniques how you can do that basically in one experimental setup. So basically, almost at a push of a button, you can switch between square lattices, hexagonal lattices, triangular lattices, Kagome lattices or leap lattices, and that's of course very nice when you want to study the different behavior of these strongly correlated systems in kind of different lattice geometries. So that's basically all at the push of a button in our hand. So in terms of interactions, what people look at, just a brief overview, we're going to mostly focus on the collisional interactions, which really happen only when 2 particles, 2 atoms come on site together. But there are also like dipolar interactions, dipolar magnetic or electric interactions that people have looked at. Of course, the famous Rydberg interactions, when you excite the electron to a very high-lying state, you get very strong van der Waals interactions between Rydberg atoms on the scale of up to gigahertz energy scales. Or you can put these atoms in a cavity and have something that are like all-to-all mediated interactions by the light passing through all the atoms in this system. So all of these have been realized, all of them are used. If you want to have a longer range interaction in your system, then certainly working with these dipolar systems is going to be interesting if you're thinking about longer range interactions also. But we're today mostly going to stay with the collisional on-site interactions in the system. So basically what we want to do, what we can do now, I think is like a dream for a material scientist, is really look into a material like this one and take photos of all the electrons in that material. So it's like, you know, you have that material, you would have an excellent microscope, and you make a photo, and suddenly you see where are all the spins on that lattice. You know, all the atoms, all the electrons, what are they doing? So in a prosaic way, you know, it's the dance of the electrons inside this material that we're interested in, and that is, of course, something that remains a dream for now for real materials, but actually for the artificial quantum simulations, this is exactly what we can do. And here's a nice picture from one of my former postdocs, Jaeyoon Choi in Korea, who did this also with lithium. It's bosonic lithium atoms here on a square lattice in this artificial crystal, and using fluorescence imaging, just shining light on these atoms, they fluoresce. When you detect them, they light up and just are like small light bulbs that you can then detect with a high-resolution microscope objective. So you can really beautifully see, we get hundreds or thousands of atoms that we can image in the system with excellent signal-to-noise ratio, determine if there is an atom at a certain position in this lattice or not. So we can do this, as I said, with hundreds to thousands of particles. We can do this in different geometries, box potentials, so no harmonic traps anymore, square potentials. We can terminate the edges of the system in defined ways, and that often, for example, it changes the behavior from topological to non-topological systems. So all of this is basically at our control by just projecting the corresponding light patterns on the atom. So you can have a lattice created by this optical lattice potential. On top of that, you can project larger lattice structures on top of that, for example, to structure the system into a box, to separate the lines of the lattice from each other, to make like ladder systems that were also introduced in Antoine's talk before. So all of this basically happens just by projecting light fields onto the atoms. So for us, for the fermion problem, you not only have the challenge of detecting spin up and down, but you, of course, also want to detect whether there's no atom or spin doublon on a side, so spin ups and downs on these sides. And you want to see actually where actually the spin ups and downs are, so not only where atoms are. So how can you do this spin-resolved imaging? And the way we've been doing it in the group is the following way that I just want to recap briefly for you. So imagine you have a physics system. This is this monolayer that you can see here. This is where actually the physics that Antoine is talking about happens. Okay, you get your stripe, your superconductor, whatever interesting phase. And then just for detection, you actually split the single plane, the single 2D system, into two 2D systems. And you do that under the action of a magnetic field gradient, so the two spin states, which have opposite magnetic moment, get pulled in opposite directions. So spin up gets pulled in the upper plane, spin down gets pulled in the lower plane. So it's like a Stern-Gerlach experiment, but now really under extremely controlled conditions. And then you have to separate the planes a little bit from each other so you can really faithfully image them separately. We do that with a charge pump. And then you just take two fluorescence photos of these atoms in these two planes. If you take a photo of the upper plane, that's the spin-up atoms. The lower plane are the spin-down atoms. And then you can just reconstruct the occupation from these fluorescence images, and then you put the two together, and this is maybe what you get in a single snapshot, a single photo that you take on one run of the experiment. So this is what comes out of the experiments, pictures like this. In the end, matrices, occupation matrices of your atoms, fermionic atoms in the lattice. So if you think about what's actually happening in this system, it's like projecting onto the configurations that you have in a many-body wave function. So if you have a many-body wave function, you have different configurations of the particles, and when you do a measurement, a strong measurement like what I've shown you before, you actually project onto one of those configurations. Which one, you don't know. It's a random process, and the probability is, of course, given by the complex amplitude norm squared in front of that part. So that means a single snapshot tells you nothing, right? You have to repeat the experiment thousands and thousands of times, and then you record in the experiment how likely is it to get this configuration, that configuration, that configuration. So we, in the end, measure actually probability of configurations, of occupation numbers. Okay, that's what we actually measure. From those probabilities of configurations, as I'll show you in a few examples soon, you can actually calculate complex correlation functions beyond simple two-point correlation functions. So it's actually a very powerful approach, as we'll see. Now, you might ask, well, what about you omitted these complex amplitudes? What about the complex phase factors? Where do they matter? They matter actually in something else. They matter in the currents that are flowing in the system. Remember, the many-body system is not only characterized by its occupations, but also by the currents that are flowing in such a system. And the currents we can actually measure by doing the following trick, by taking the physical system. This is the 2D system, again, what Antoine's talking about. There will be some currents flowing, or some occupations. And now by actually separating this system, projecting it into an array of double wells, we can actually now manipulate those double wells and measure the currents on these bonds that I show you here. So how do we do that? Think of the double well as, again, as just another incarnation of the two-level system. An atom can be on the left-hand side, on the right-hand side. It's like spin up or spin down, right? And so basically, you can now have tunnel coupling between left and right. This is like a sigma x rotation in the kind of orbital Bloch sphere. Or you can tilt the double well and detune the different sides from each other, and this is like making a z rotation on this Bloch sphere. So you can now think of this two-level system just again as states on this on these two sides, on this double well being states on a Bloch sphere, on an orbital Bloch sphere that marks the different configurations that you can have here, the coherences in the system. And it turns out in the z direction, it's basically the occupations that you're measuring. If you're looking in the x direction of your Bloch sphere, you're measuring the kinetic energy operator. And if you're looking in the y direction, you're actually measuring the current operator. Okay. So how do we do that then in practice? So for example, if you want to measure the current operator, when you read out only density. So you have to map current to density. Well, we can map current to density by just doing a pi/2 rotation around the x-axis. Then we basically map the current operator into the density operator. So by just doing that operation, just doing a sigma x rotation, for the right amount of time, we can tune this cosine factor to 0 and the sine factor to 1, and then you see what you're reading out as a density difference after this time evolution is just the current operator. Okay, so this just shows how these rotations on the Bloch sphere give you basically access to all kinds of orbital degrees of freedom, all kinds of operators, and if you add, for example, a sigma z pi/2 rotation, then you're not measuring the current operator, but you're measuring the kinetic energy operator. So that's nice because now you actually have access to all energy terms in your Hamiltonian. You can measure kinetic energy, you can measure through the occupations the interaction energy of your fermionic system, which means you can actually also think about reconstructing the entire energy and actually also fluctuations in these terms in the system. All right, I just want to show this, that this actually works when you're setting up some interesting current patterns in the system. So we used kind of Floquet modulation to just imprint artificial phase factors, artificial currents onto these systems. And then we just used the technique I showed you to actually measure out those currents. And you can see here the current correlation functions that we measure in the experiment and what we expect from theory by just imprinting a simple current pattern onto the system. And you can actually see that this actually really works extremely nice in the system. So this actually allows us not only to measure locally different terms, globally different terms, but also do this locally. For example, if we want to measure in one term the kinetic energy operator and the other one, in the other double well, the current operator, well, then we just have to interleave a z rotation locally on one of the bonds where we want to measure another operator. And this is actually easy by just shining a light shift on just a single bond, on just a single side of the system, which basically leads to this interleaved z rotation on your orbital Bloch sphere. And then you're a situation indeed where on this bond, for example, you would be measuring kinetic energy. On the other bond, you would be measuring actually the current operator. So locally having these z light shifts allows you to locally control what kind of orbital operator you actually want to measure in the system. You can also use this for state engineering, just as a side remark, for creating interesting initial states by just, again, making use of the fact this local detunings allow you to have different local dynamics in each of the double wells, and you can have them, for example, then run 180 degrees out of phase by introducing this light shift bump here in the center. And if they run 180 degrees out of phase and you wait for the right amount of time, when these will have tunneled from left to right, the next well will have tunneled from right to left, and then you can see these stripe patterns emerge in the system. So you can also create different kind of patterns of initial states in the system, and if you make more complex light shifts, project more complex light shifts onto your two-dimensional system through, for example, digital mirror devices, you can set up kind of arbitrary complex patterns and structure your system as you want. Just as a final remark, showing that this actually works nice even for large systems. This is on one of our boson experiments where we're really looking at 140 plaquettes, so 2x2 arrays in the system that we decouple from each other, where we imprint kind of we turn on an artificial gauge field, and we can actually locally resolve the cyclotron orbits on these plaquettes. So these atoms exposed to artificial gauge fields, artificial magnetic fields, making basically local cyclotron orbits as electrons would do in a real magnetic field, actually. So, and this just shows you that, with these experiments, I think it's exciting because we can have this spatial resolution of the microscopic currents and current correlation functions also in these systems that allow us to access, very complex current distributions on these systems. Let me actually skip this. For those of you who can ask me, we actually use this also now to go to strongly interacting flux ladders. And I think it's interesting to look into this again, looking again at Meissner effect with strongly interacting bosons. And eventually, I think this is an excellent starting point for actually in the future also looking at fractional quantum Hall phases. If the temperatures can be lowered a bit more, factor 2 to 3, then you should be able to see kind of interesting interacting topological phases, and having this current resolution will of course be extremely interesting in looking at those systems. All right, so now let's turn to the fermions after we got used to what you can do, what you can measure in these systems, occupations, currents. Let's now use this actually to look at the physics of the strongly correlated electron systems. And you've seen this diagram also in Antoine's talk on the phase diagram of the cuprates. And we've also started in the discussion with the zero doping case, the antiferromagnetic Heisenberg order that emerges here. And then when you dope the system, here you see all these kind of phases emerge, the pseudogap that was talked about, the strange metal phase, the E-wave superconducting dome. And what we are trying to basically understand in such systems is how dopants that we put into the antiferromagnet interact with this background magnetic order. And we can use now the tools of this microscopic images of looking at these processes really at a microscopic scale, what's happening when we put holes into the system and look at their interplay with the magnetic order. So how do we do that? Actually, here comes again a proposal from Antoine from actually now 16 years ago already, how to do that, how to create such a system. So you would actually, a good idea would be to actually have a physics system. This is this plateau where the lattices are working in over the entire system, but here a flat region, this is your physics region, connected to reservoir regions at a higher energy. And now what you can do, and all this is just created, remember again, by projecting light patterns onto the atoms. And now what you can do, you can just change the intensity of your light field in the center relative to the reservoir, and that would mean that you're making this mu r, this chemical potential, deeper. And that's like basically tuning a voltage on your real material and tuning through the different phases that you can get by tuning in and out of those phases by applying different voltages and tuning the Fermi energy, for example, in these systems. So we can do the same thing. We can tune the chemical potential by just changing this height of the potential here. And if we, for example, tune to the right value, you can see here that you get a nice mod insulating phase, which is characterized by this 1 fermion per lattice site. So the average density is really beautifully 1 fermion per lattice site. And the variance, if you look at the compressibility, for example, the variance is extremely low here, showing you have very low number fluctuations. And on the outer rim in this reservoir region, the density is around 0.2, 0.3 fermions per site. So that's a metallic region that's coupled to the mod insulating region in the center. What I always find really quite remarkable in these pictures is that if you look at the transition from mod to metal, this happens within 1 lattice site radius. You know, within 1 lattice site, you transition from this MOTS phase to the metallic phase, and you can really spatially resolve this transition ring, where this transition is actually happening. Okay, so now we've established we have a mod insulator, but now we want to see that it's also antiferromagnetic correlations persist in it. So for that, we basically split the system and do the spin detection that I showed to you before. And if we then do the images, put them together, and calculate from these snapshots the spin-spin correlation functions, this is what you see. Okay, so you see indeed there's also a nice antiferromagnetic order underlying this mod insulator. And with this antiferromagnetic correlations, we can plot them here on this graph. And then we can go to people like Lode Pollet, and he can run this determinant quantum Monte Carlo method that Antoine was introducing to you, and that this DQMC gives the blue line. And actually from the blue line, you see we have a perfect match with the experiment for a certain temperature. All the other parameters are ab initio fixed, so we know the U, we know the U over T, we know what the small t, the hopping over exchange coupling is. All is known. There's only one parameter that is free, that is the temperature. What is the temperature? So we take the one where we find match between experiment and theory. So that tells us that's actually how we do thermometry. And actually, that's not so easy to do thermometry in other ways away from this point. That's actually a slight problem of the field right now. It's not so easy for us to put temperatures, especially in doped systems, reliably. Okay, but here you can see it works well in the undoped case. We get a very good match. The system seems to be thermalized, and we can extract the temperature from this graph. And you can see it was in the regime here of 0.25. This is, I think the lowest we've had was 0.2 in our experiment. So these are kind of typical low temperatures that we could reach in these experiments. So now let's put a single dopant into the system. Let's see what happens for a single dopant. And I don't know, did you talk about the physics of the polaron already or not yet? Okay, so what happens now if you put a single hole in that system and it wants to move? So if that single hole actually wants to move, it can hop from one side to the next side, and then this green spin will move in here, and then it hops one side more, so the red spin moves in here. And what you see, what actually happens is that after this movement of the hole, it actually leaves behind a aligned ferromagnetic array of spins. So that's not good from the magnetic point of view of the model. The magnetic model favors antiferromagnetic correlations. So actually here it leaves behind an energy cost of flipped spins that grows more and more the further this hole actually moves. So that already tells you this hole cannot move indefinitely through the system because it would cost an indefinite amount of energy. So it has to be somehow tied, bound to the original site where it started. And this is indeed what we call, that's this spinon over here that remains is tied to the holon over here. And they cannot separate arbitrary distances from each other. They in fact form a new quasi-particle. And the situation is very much like in nuclear physics, where you have a similar phenomena where the energy cost, for trying to separate quarks grows linearly with distance. So you have confinement. And the new particles that form are the partons, the mesons, for example, in nuclear physics. And the same thing happens here. You have a new quasi-particle that is formed out of this hole, tied to the spin background, and this is what we call the magnetic polaron. And the magnetic polaron basically is this impurity, the dopant, surrounded by a cloud of modified spin correlations relative to the background. Okay, so whenever this hole moves, it doesn't only move as a hole, it always moves as a compound object of this cloud of distorted spins surrounding it. So now with quantum gas microscopy, I think we, for the first time, really were able to take pictures of this polaron in real space to show this, this deformation of the spin background in the vicinity of the dopant. And here's actually a nice picture from one of our recent works with Thomas, where we basically now look at the following. This is a 3-point correlator. So remember, we're doping the system. In this case, we're actually doublon doping the system, so with an extra kind of atom there. And this doublon can move entirely freely through the structure, through the 2D system. So you never know where it's not going to appear. It's not pinned to any site. It can move completely freely. And in a single snapshot, of course, you will find it somewhere. You make a snapshot, the wave function collapses, you find the doublon somewhere, and then you recenter your coordinate system around this doublon, or hole, if you do hole doping, and ask how are the spin correlations modified around this hole. Again, we do this for thousands of shots. We recenter the coordinate system on the dopant and look at the modified spin correlations around the dopant. And then we can plot what is called here the connected correlation function. This is the difference of the spin correlations relative to the standard antiferromagnetic spin correlations without a dopant. So what you're already seeing here is what the difference of spin correlations is relative to the background antiferromagnetic correlations. And you can see beautifully that there's this really nice cloud, distortion cloud of modified spin correlations surrounding this impurity. And it's actually not such a small object. So it's like measuring the kind of the internal structure of this magnetic polaron. And for that, to measure something like that, you really need to be able to measure this 3-point spin correlation function, because you're conditioning the spin correlations that are indicated here by these ellipses, and the strength of the spin correlation is given by the color. Positive is red, negative is blue, but you're always conditioning it on finding a hole in the center and then measuring what the spins are doing, in the vicinity of that hole. So that allows you to measure this polaron structure in the system. So now, of course, we can readily, continuously tune the doping in the system and see actually how this polaron is actually destroyed. So if we look at the spin-spin correlations, this whole spin-spin correlations, we actually see that these kind of vanish around pretty much a doping of around 20%. We basically just get a free dopant with no kind of polaronic spin correlation surrounding this impurity anymore. And this is basically in this cartoon picture now. If we go back to our phase diagram, we are now in the following situation. We start with the antiferromagnet. We dope very little. Polarons form. These polarons are positive charge carriers. They are the charge carriers that form kind of the metallic state here. Then there's kind of a crossover region where this polaron breaks down for larger dopings. And eventually, for very large dopings, you just end up with a standard Fermi liquid where just the normal electrons are, again, the charge carriers in the system. And you can really now precisely map out the crossover from this polaronic strange metal phase to the Fermi liquid phase based on these microscopic pictures in the system. All right, so now let me switch to the pseudogap that Antoine was talking about and show you a little bit of some newer work that we've been doing in this direction, trying to understand the pseudogap, not through spectral functions, which is something we've been talking about here, the gap in the spectral functions, but emerges, but again also through the light of actually correlation, microscopic correlations in the system. And that may bring you back to, again, to the original discovery of the pseudogap. Remind you again that the original discovery of the pseudogap was done by looking at the spin susceptibility and finding that there's a maximum in the spin susceptibility in the systems as a function of temperature. Yeah, so when you lower the temperature, a maximum, this first rises and then it lowers again, and this maximum point, that was actually identified as the entrance into this pseudogap phase. Okay. We see this also in numerics. So this is from Alex Vitek, this METS method that Antoine also talked about before. Very beautifully, you see that if you working in the system, you lower the temperature, you see a maximum emerging, just as you see actually here in the experiment. And one finds that actually this occurrence of the maximum agrees actually exactly with the emergence of the spectral gap that Antoine was talking about in the spectral function. So this is maybe more what's associated with a gap emerging, pseudo gap emerging in the system, that at the antinodal points, you have a depression of spectral weight and the opening of a gap at these points. Okay, and this occurs synchronously with the T star that you find up here in the magnetic spin-spin susceptibility in the system, this maximum occurring here. All right, so we basically have our spin-spin correlation data. We can do this for different temperatures. We can do this for different dopings. And here I just show you different spin-spin correlation data like I showed you in the beginning already, what we had when we compared to the quantum Monte Carlo simulations. So we do different temperatures. We do this for different dopings. These are the green, different shades of green that you see here in the system. And first of all, we can see, okay, do we agree with theory? And we can look with the determinant, quantum Monte Carlo, and also the METS method, and we can see actually it works actually extremely well for kind of most of the parameter regimes that we looked at. We have very, very good agreement with the theories that still work very well in this regime. And now we take this data for a large variety of dopings at temperatures, over 35,000 shots, where we varied the doping, the temperature at this moderate interaction strength here of U over T 6.5, and we characterize how much kind of magnetization, staggered magnetization we have in the system, so how much antiferromagnetic order we have. We can plot that through this staggered magnetization, and we can come up with this two-dimensional map that we see here in the system. All right, so let's look again at these individual curves again. I'm plotting just the different spin correlations and the correlation length here plotted as a function of temperature in these systems for different dopings, and it looks very messy. You don't see any order in the system. So now we came up with the following idea. Let's try to replot the data by introducing a new energy scale and see, just doing a linear expansion which depends on doping, and just thinking of this energy scale as some function of doping, and just doing some Taylor expansion. And can we find parameters here that if we replot this data, that the data collapses? And it turns out this actually works extremely well. So we look at this data, we replot it with this new energy scale that we find from actually collapsing all the data. You see also on this log-lin plot, this agrees very, very well with the correlation length following exponentially increasing function. And we see that for the right parameter here, for the right Taylor expansion, actually only the first order term is actually the relevant term. The second order one is already very small. We can see that all of this data basically collapses. Okay? So just by finding this universal behavior, we find a new energy scale, or put it the other way around, replotting the data in this universal energy scale delta actually gives us universal behavior of the magnetic correlations in the system over all kind of different doping degrees of freedom. So now we can compare this empirically found energy scale delta, depending on doping, with T star from METS. So T star was the maximum in the spin susceptibility, and this is actually shown here. So the T star data from METS, where the maximum in spin susceptibility occurs, which is kind of the classic hallmark of entrance into the pseudogap phase, actually agrees precisely with what we find with the kind of empirical functions when these kind of correlation functions all collapse onto each other. Okay, so now this leads us then to the suggestion that actually what this newly found energy scale is that collapses all the data is T star, meaning that, said in other ways, if you're below the pseudogap, if you enter the pseudogap phase, you have universal behavior in the scaling of the magnetic correlations if you replot them in the right way. And we looked at this not only for the magnetic correlations, we looked at this also for higher order correlations. So for example, for charge spin-spin correlations, these were the polaron correlations. We again see the data is a bit more noisy, but you again see it actually collapses onto each other. And for the spin-spin, fourth order spin correlations, again, if we replot everything with this T star or delta energy scale, we see a collapse of these kind of correlation functions in the system. So I think this gives us kind of a new, kind of interesting phenomena that we observe that we can use either to see that there's pseudogap physics emerging, or you put it the other way around. Whenever you enter the pseudogap, we actually find that there's a universal behavior, universal scaling of lower and higher order spin charge correlations. Okay? Now, how this persists, so to kind of even higher orders and even lower temperatures, this is an open question, but I think this is a new discovery that was not known before. It can be reproduced by the theory, so numerics also sees this, but kind of a new way of looking at the entrance into this pseudogap phase by this universal behavior of the correlators in the system. So this puts us now in this, I think, very interesting regime. Where do we stand? So Antoine talked about it. We established we can enter into this pseudogap regime. With the newest experiments from Marcus, it's shown that you can go down here at 0.1 temperatures of the hopping. So this puts us, of course, in this extremely interesting regime, which Antoine also was mentioning is extremely hard to calculate things on, where we can do experiments now and have this microscopic correlation functions that we can measure and put them together with theory. So this is, I think, an extremely exciting moment for the community, because it allows us also to introduce these new microscopic real space quantities and actually connect them also to macroscopic thermodynamic quantities of real materials. And I hope this will help to shed light, I think, in the future, what the nature of this pseudogap regime is. If there are hidden order parameters that maybe you couldn't just reveal so far because, you know, if you looked with two-point correlation functions, you just could not see this hidden order, which only manifests itself in higher order correlation functions in the system. So this is something, I think, where we have great hope that this will be a very exciting direction for the next months and year to come, to look in this direction, to search for this, and to really have a better understanding of this finite temperature phase. And then, of course, eventually, if we can push even lower down, see this transition into this stripe phase that Antoine was mentioning also about, to see what is the nature or the crossover or phase transition from whatever pairs or interesting charge structures you have here into this stripe phase. I think this is really now many, many open questions, as you see, but also like really new approaches that hopefully together with theory will allow us to answer these questions. All right, just one comment quickly on another system we've been looking at when we try to actually introduce charge structures and binding of particles at even the energy scales, temperature scales where we are. There was an idea from Fabian Grust and Annabelle Bort to actually that mixed dimensional setups could be very efficient ways to boost this energy scale for high TC superconductivity. And why does that actually work? I'll tell you in a second. So mixed dimensions means you have, for example, a bilayer system where when you dope the individual layers, the holes, the dopants, can move within each layer, but they cannot cross between layers. So, and spins can talk to each other in 3 dimensions, so spins talk to each other across layers and within layers. So spins is kind of a 3D setting, but holes or dopants only move in 2 dimensions. So that's what we call a mixed dimensional setup, mixed dimensional motion for the holes and the spins in the system. And that actually allowed us to boost the pairing energies of the holes. I'll explain that to you in a second, why, in intuitive picture, why that works, by almost a factor of 15 compared to the normal, kind of normal dimensional systems. And actually also in the 2D setting, observe stripe-like structures where kind of holes, for example, tend to align along these density structures, but not yet low enough temperatures for the stripes to form into regular space structures that we could see them also in the magnetic structure factors in the system. So this is actually connected to a very interesting new material class that people have been talking about in high-TC community, the so-called nicolates, which appeared just, I think, 2 years ago or so in the community. And when people analyzed the band structures of these systems, they actually found, well, actually in these nicolates you also have such mixed dimensional configurations with holes not being able to hop across these layers and spins talking to each other in 3D. So it's actually not just an academic setting, it's a real very interesting new setting, how you can push, how you can boost high TC to higher temperatures using such mixed dimensional setups in actually real materials. So let me just give you a very quick explanation why that actually works, how you can actually tune these. And let me just remind you again where actually hole binding or pairing of holes comes from in these systems. And actually it turns out this originates from entirely magnetic correlations in the system, because remember, there's no attractive force in the underlying Hamiltonian. Everything is repulsive in the repulsive Hubbard model we're talking about on the microscopic scale. So it's best understood in a ladder system like the one that you can see here, where if you would have, for example, strong antiferromagnetic coupling between the spins on a rung here, they would tend to form rung singlets. So you have singlet structures forming here along the rungs of the ladder. And let's imagine you put 2 holes into the system, and now one hole starts to move here. And if one hole starts to move, it will actually break the singlets. The singlets are now tilted, and that breaks them, and that costs you energy. So that's not good. So in order to unbreak this energy cost, the second hole can follow in pursuit. And if it follows in pursuit, it actually undoes the damage the first hole has been doing while moving through the system. So when they move together, it's good energetically. When they move separately, you always have a high energy cost in the system. And this actually leads to a pairing of those holes with an energy scale on the order of this exchange coupling along the rungs, G-perp. Now there's one thing we're missing. The argument is a bit too naive, because what you're missing is, from a kinetic energy point, it's not good to have the 2 holes together, because from a kinetic energy point, holes want to delocalize to minimize their kinetic energy, and if they sit right next to each other, they can't do that, right? There's already another hole there. So from a kinetic energy point of view, this costs a lot of energy. From a magnetic energy point of view, it's good. And it turns out then that for real systems, for real ladder systems, when people do the calculation, the binding energy of the holes is extremely weak. Because you're not getting this full magnetic energy cost of binding, you have this repulsion because of the kinetic kind of Pauli kind of blocking, if you want, of the holes. And that leads to an extremely small binding energy of the holes, very weak binding that you see. Now if you go to the mixed dimensional setup, you see that's great, because in the mixed dimensional setup, holes cannot delocalize across the rungs. So there's no kinetic energy penalty. So you take the kinetic energy penalty away, and you only have the win of the magnetic energy cost. So at that point, you get now the strong binding and the strong boosting of the pairs that form in the system. So that's basically the intuition behind this. All right, let me just, before I cross over to a new topic, let me just mention a few other kind of exciting topics that other teams have been doing in the community. There's really beautiful work from Martin Zwierlein on the attractive Hubbard model, which we heard about also. And then there's on these kind of non-standard lattice geometries on tunable frustrated systems with triangular geometries. Markus' group and Wasim Bakar's group have really done wonderful work in this direction. And out of China, Janwei Pan's group, they're really now able to realize super large systems, three-dimensional systems with almost, 100,000 particles in these systems at very cold temperatures. So I'm sure we're going to hear, as often now in China, a lot of very interesting stuff coming out of that direction as well. All right, let me switch to another topic and actually combine both in the end of the talk, going from analog to digital. So far everything I told you is analog quantum simulation. We prepare the system, we look at it, but what about if we think about using like gates based on fermions to do kind of calculations, material science, chemistry calculations? Well, what would be the advantage of doing that with fermions? Well, one advantage of doing everything with fermions right away is that all quantum numbers that are conserved are automatically conserved. Because you're working with fermions, you're not going to violate any quantum numbers that are relevant to fermions in the system. Whereas if you have a spin mapping, you can always go out of the space of valid conservation numbers, and basically then your calculation is ruined. So you can be more efficient also with fermions, but intrinsically I think the biggest advantage would be that you're preserving these relevant quantum numbers in fermionic problems. So to do that, what do we need to implement in the system? We need to be able to do single qubit rotations, single spin flips in the system. And we're able to maybe move atoms around. This is what we could do, for example, with the superlattices, with the orbital degrees of freedom that I showed you. But then we also need to think about gates, collisional gates that we could do between the particles to realize all the ingredients that we need for such a digital operation for the fermions. So let me first talk about the single qubit gate. Again, this can be also very interesting for the quantum simulation community. Basically, what you want to do, you want to be able to flip a single spin in your many-body system. So you focus your laser beam on a single site and you flip a single spin. So how can you do that? We're working in lithium with these two spin states that you can see here. In the electronic spin, they're pointing downwards, and the nuclear spin, they are separated from each other. So these are the two spins we're working with. And one way to do a spin flip is actually to do a following trick, to do a microwave transition here to one of these states here, where the electronic spin has been flipped, then use a light shift focusing a UV laser beam onto that state to make a Z rotation by pi, and then to undo with a pi/2 pulse again this initial kind of spin flip from here to here. So this would be the operation that you do. You first flip onto the equatorial plane, you introduce a light shift, then you undo the flip, and for the case where you didn't focus your laser beam, you're just going to go down again, and for the case where you actually now had the pi rotation around the equatorial axis, you're going to flip the spin into the upper axis. So this should allow extremely efficient single qubit rotations in the system, and we're going to do that with UV beams to really locally focus onto the individual lattice sites to see the individual lattice sites very, very nicely and resolve them very nicely in the system. Actually, one interesting thing is we're also planning a magnetic field setup that should have 10⁻⁷ field stability. That means actually also for doing spectroscopy in a many-body system, we'll be able to do that to fractions of the tunnel coupling of about 1/100th of the tunnel coupling. So I think that's interesting to keep in mind also for those. For the kind of gate operations, if you want to do gate operations, you can basically now look into collisional gates between the two spins on such a double well that you want to have. Now, what is the Hilbert space of the fermions on this double well? So while it's a 16-dimensional Hilbert space, it breaks down into different particle number conserving blocks. There's 0 particle, 1 particle, 3 particles, 4 particles, and the most interesting one for us, the 2-particle sector here. And this 2-particle sector here consists here of this case where you have 1 fermion per lattice site, be the spin up, spin down, or kind of this kind of spin triplet sector. Or you can have here the doublon sector where you have 2 particles on the left lattice side and 2 particles on the right lattice sides in the system. So these are the blocks, the block structure of your Hamiltonian, and now we want to realize gate operations, for example, in this kind of structure in this part of the spin qubit Hamiltonian, or gate operations in this kind of doublon part of the Hamiltonian. So this is, of course, nothing but the super exchange processes that Antoine also talked about. So this would be just a super exchange process, and this would be a correlated double-on hopping process, hopping two particles from the left side to the right side, again happening at the scale of the super exchange scale t squared over u in the system. So let's do the experiment. So we take our fermion system, we separate it into kind of double well operations, and then we can apply this kind of continuous time evolution, for example, for the swap gate, for the super exchange gate, and then monitor the population of left and right well as a function of time. So we start out with everything on the left-hand side, spin down, spin up on the right-hand side, and then we evolve for a full swap operation. Then you see how the spins have been swapped. The spin downs have moved to the right, the spin ups have moved to the left, and in the immediate time, you would get an entangled state between the fermions on the double well. And then we can look how good is the quality of this operation, how good can we actually perform this gate operation, this swap operation. And it turns out it works extremely well. So if we look at the time evolution of the swap operation, we find actually fidelities here for a pi pulse of over 99.9% fidelity for the pi pulse of the swap operation occurring in the system. That already gives us an idea how good gates could be. Now, this is a continuous time evolution, and if you want to think of gates, then you have to take into account timing errors that can occur in the system. So in order to do then a fair comparison, we really have to do also time evolution, time gate operations in the system. So again, how can you do this? You want to avoid coupling the sectors of singlets where you have single occupations to the double-on sector, the two-particle double-on sector that I showed you before. So in order to avoid double-ons appearing in the system, you can do three things. Number one, you can go to very strong repulsive interactions, which just suppresses double-on formation. But then you have the problem that, of course, the gate operation will be extremely slow. So remember, the J energy scale is T times T over U. And if you go to very small T over U values, very large U over T, then you will have extremely slow gate operations. Then there was a trick that was introduced by John Vaipan's group a few years ago. If you go to very low U over T values, you can actually go have a fast dynamics, and if you go to this very special ratio of U over T of 4 over square root 3, then you can realize a fast swap operation where the spins are swapped at this point in time, but at the same point you have a point where the double-on population also is 0. So double-on population oscillates, spins oscillate, spin exchange oscillates, and because they make a commensurate oscillation, you can find a point in time at this special ratio of U over T where at the end of the gate you would have no double-ons and the spin swapped in a very fast kind of gate operation in the system. Now the problem there is, of course, that this is very sensitive to timing and interaction strength errors in the system, so maybe not so ideal as well. So we kind of came up with a balance of both. So we actually ramped to low U over T values, so you can be fast, but we do this in a way that we first are fast and then slow down by just going to simple Blackman pulses. And you can see that with the simple Blackman pulse, you can have fast gate operation, which completely suppresses double-on formation in between, but still allows very efficient swapping of the spins in the system, very efficient gate operation in the system. So we can measure, for example, the fidelity of these gates by applying multiple of these swap gates. And if we do that, we find that this gate fidelity is around 99.8%. And I think that's, for neutral atoms, very much record values in the system, very comparable to what's been shown in the Rydberg systems, but now entirely through these collisional gates in the system. We can also prepare we stop with the swap gate at half of the time of doing the swap operation. We end up with this entangled state in the system that you see here. And we can check what is the lifetime of this entangled state. And because we're working with these two lowest states of lithium atoms, which have only a nuclear magnetic moment splitting between each other, we should have extremely low decoherence times of this entangled state that we create in the system. And when we measure this lifetime of this entangled state via kind of singlet, triplet oscillations by applying a magnetic field gradient and looking how we create, how we change the entangled singlet states to triplet states and back, we can measure that through this oscillation function. We can see that we get a coherence time of these entangled states of over 10 seconds in the lattice, showing with the gate operation on the 10 kilohertz scale, And 10-second lifetime is an extraordinary quality factor that we can realize in these systems of gate operations and coherence time. We can also do that in the pair hopping. I just show you the data for that. Also, the quality is slightly different because slightly worse, because there you're also sensitive to the tuning errors in the system. So it's about a factor of 2 worse there, the quality factor of the oscillations. And the reason is because in these pair exchange processes, you're immediately sensitive to any kind of local detunings, any local disorder effects, where a super exchange, this only enters actually in second order in the system. So why is this interesting? So what is the architecture we're thinking about? And this is something that Philip Price was actually instrumental in thinking about together with Covestro, that you can basically now think of putting all these building blocks for fermionic quantum computing together, where you have the local spin flips, you have the exchange gates that I introduced to you before, and all of that should allow you basically to realize a universal fermionic quantum computer with these gate operations. Now, another thing where I think these are going to be interesting, which is maybe more interesting to the quantum simulation community, is that these gate operations will also be very interesting as new tools to reveal complex order parameters. And this was shown in 2 papers here, one by Fabian Grust and Annabel Bort, and other one from Susanne Yelin and Sun-Woon Choi from MIT and Harvard, where they basically showed that in order to measure the order parameters in such systems like these nicolates, these bilayer systems, we can actually make use of these gate operations to actually read out the order parameter directly, to measure directly the superconducting order parameter by a sequence of only global gate operations, global control operations that we are using in the system. For example, just global microwave rotations together with the gate operation that I showed you are then sufficient to realize these, to measure actually directly, for example, D-wave order parameters in the system. So I think this is, of course, a big question. How do you actually detect superconductivity? But the gate operations I showed you actually will be the way forward to actually do that in actual experiments. All right, so let me finish and showing a little bit, where are we going next in the experiments. So I hope I convinced you that, on the analog side, we have extremely powerful systems now. The temperatures are in regimes where they are really challenging theory, going to push us into completely new regimes also in physical understanding of these systems. In the numerical side, a lot of limitations occur also either in dimensionality or in temperature and doping that one has to deal with. And now I think for the first time we can have these precision experiments in a regime where I think we can really talk about quantum advantage or potential quantum advantage between experiment and theory. And I think the digital mode is interesting maybe for the digital quantum computing that I talked about, but also having these digital control knobs for readout and preparation and measurement schemes. I hope I convinced you these are extremely valuable tools to go beyond like measuring simple occupation numbers in the system and really, for example, measuring order parameters also. So finally, let me say, if I look a bit forward, one extremely interesting regime that we're working on in different experiments is combining the world of optical tweezers with the world of these optical lattices. And Adam Kaufman is one of the pioneers in the system, just to show you one of the pictures how large these systems eventually can become. These are strontium atoms on a really huge lattice with over 25,000 lattice sites, over 10,000 individual strontium atoms there. And now we're going to come in with tweezers and sort these atoms in this optical lattice to create different configurations. And one thing that we did, we were able actually to operate such an optical lattice continuously for basically arbitrary amounts of time. So let me just show you this nice animation. So what you see on the left-hand side are atoms that are stochastically loaded into optical tweezers, so completely randomly loaded into the tweezers. There's a lattice underlying the entire structure. And we can move atoms from these tweezers into lattice positions and hold them there, okay? So we just, if you go to the beginning of let's go maybe again back to the beginning. This is that we start to build up the array. We bring more and more atoms from the tweezers to define positions on the lattice. So we build up whatever structure we want here. And whenever you lose an atom on the right-hand side here, you can actually detect that and replace it with another atom that you bring in at the right point in time. So this is, of course, interesting for creating different initial states in optical lattices, different configurations with this local control, speeding up cycle times. It can also be interesting for metrology experiments, but of course also for quantum computing. This is obvious, interesting applications if you think of these blocks as maybe encoding logical qubits that then will be brought into interaction with each other and scaling up, making use of the scalability of this lattice systems combined with optical tweezers. So so thanks for listening. I think I should give the credit to the tremendous, exciting group of people I've had the pleasure to work with, namely Thomas here. So he played an instrumental role in all the experiments that you've seen here, especially on the pseudogap. He was one of the leading figures there on our fermion experiment. Titus has taken over now from Timon, who's moved on to a position in Strathclyde. Philip is leading the team on the Fermi QP experiment. This is where we want to go a little bit more in the quantum computing direction. And we've had this wonderful collaboration between Antoine's group, Alex's group, Fabian, Annabelle, and Lode. And I think these are just, apart from being wonderful people, that each one of them is experts in one specific numerical method. And I think this really shows also how bringing people together from these different numerical methods help us to do precision physics, do precision measurements on these many body systems, and hopefully together with theory advance our understanding of these systems. Okay, and with that, I should give credit also to the cesium team where I showed data in the orbital degrees of freedom. This is together with Monika Eidelsberger on our cesium experiment, and the key person on the orbital degrees of freedom was actually Alex and Petro doing those experiments. All right, so with that, thank you very much for your attention.